this is the thing that we have started yesterday. Yeah,
We are getting
you're
white
not able to
screen.
see the screen.
Yes, sir.
The screen is full white, sir.
It's white, huh? Why is it white? Let me check once again. I'm providing my entire screen, so this is the entire screen. Now I'm trying to open my presentation. Now, could you see the presentation?
Yes,
Yes,
sir.
sir.
Yeah.
Yes, sir.
Yeah. So in last class, what we have tried to understand is the basic types of errors that we will get while we do some experiments or measurements. And I have told you that in broad classification, we classify our bias errors, and then the other one is random errors. We have in length understood that systematic errors, because of the inappropriate maintenance of the instrument, that means if we are not properly maintaining the instrument, it may come over a period of time. They generally tend to produce errors, and those errors that come with in a systematic way can be eliminated, because an experimental is an experimental error. But if we know what is that error, then the error will not be no longer any error. Have you understood? If we know what is the error, we can eliminate that, right? So that never becomes an error. If you don't know what is the error, then only the problem is. If we know that there is a deviation, and we know the value of the deviation doesn't affect our result. We know whether to add or whether to delete, so that such that we will get back to the true value. That is what I want to convey. Okay, so systematic errors can be eliminated by doing calibration. Okay, and how they will come into picture, we have by the based on the experiment, it varies. Based on the experimental conditions, it varies if you are not following the same things. But easily, what I can understand from that is, it will always go in one direction. It will not be in random in nature. Okay, if it's showing an increased value, it keeps on increasing very slowly or very steeply, or it may be with a different slope. It may be increasing, or it remains constant sometime, then increasing constant for some, and then that also can be seen. Okay, but it's not that for some time it increases and sometime it is reducing, and then that kind of variation you will not see if it is a systematic error. I hope I'm clear. And then I have shown you one example where which will be called as gross approximation, or we can say that it is by our basic common sense. How do we estimate that error? By common sense. If we know the deviation in a equation, what we do is simply we try to find out the maximum error and the minimum error, and by putting that maximum and minimum error in the function, we will try to find out what can be the maximum error percentage and minimum error percentage. That's a gross approximation. It's not an accurate method, but we will be somewhat very quickly, if you want to give a value, we can use that. Okay, so that is basically what we do with what we call as systematic errors. When it comes to random errors, we have to use statistical means. Why we are using statistical means? These are random in nature. How they behave, it's not possible for us to estimate. It will not go in one particular direction. It may go in any other directions. Okay, so it may be increasing, it may be decreasing, it may remain constant, it may increase by a proportion for some time, and then it varies in different proportions. It may reduce in different proportions. That all the things may happen. So if we want to find out for such things, if it is a single sample experiment, there are two ways of looking at the samples. One is single sample and the other one is multi-sample. Let me give you a brief example for single sample experiment. Single sample experiment means if you are taking pressure measurements. For example, we are trying to measure different pressures with the same instrument. Okay, we are not changing the instrument. Suppose if I put the instrument, same instrument, and we are trying to measure. So how many times we do the experiment, it almost gives the same value. So that is a simple sample experiment, single sample. So the sample will not be too different. When it comes to multi-sample experiment, we kind of, first set we will do with one instrument, second set we will do with another instrument, third set we will do with another instrument. There are multi-samples by different instruments. And by doing suitable statistical analysis, we can reduce we can find or determine how much deviation that measurement will have. Okay, that measurement will have. So that is basically your multi-sample experiment. So multi-sample experiments, you can always use the statistical analysis, but single sample experiment sometimes it will become difficult using the statistical analysis. Okay, but the costs incurred will always restrict us to go for multi-sample experiment. As an experimentalist, buying one instrument and measuring itself is difficult. So again and again, with the different instruments and all is not possible. So the basic statistical ways by which we measure the random random error, I am giving it out here. Okay, so the primary concern here is we have already looked at these fixed errors, okay, or systematic errors. How do we eliminate them? We try to find out, or we try to evaluate how much is the systematic error by careful calibration of the instrument, by comparing the instrument with a system which has precise known inputs. We compare with that system and try to find out a mathematical equation, and then we will be able to reduce the error, or we will be able to come closer to the true value. So that is basically eliminating the systematic error. But when random error comes, we never know what is the reason that the error is getting into the measurement. So the major concern is applying our probability and statistics to analyze the experimental data. Okay, so when a set of readings of an instrument is taken, the individual readings generally will vary somewhat from each other. For example, if I'm trying, as yesterday I told you, I try to measure, I try to throw a stone to a nearby pole, which is far away. So every time if I'm throwing it, what happens is sometimes I will go to the very close, sometimes I will be far away, sometimes exact position. Likewise, we will get for the same instrument, with the same instrument, there will be a lot of different readings that we get. Okay, so in such a case, if we are measuring certain instrument and then it's giving individual readings which is varying somewhat, what we will do basically is we will try to find out the arithmetic mean, median, and mode. You might have known in your +2, in your JEE also you might have studied mean, median, mode. For example, there is a class and the class exam is for 100 marks, and each student will score differently. Okay, so if you want to find out in one single value, if I have to say that most of the students, maximum number of students, how much they have got, we will generally use the central tendency. So we will try to find out where is the center for all the scattered data, right? So someone will be getting 35, someone will be getting 100, someone will be in between 40, 50, 60, 70, 80. And mostly, if you look at the way, there will be a cluster of students, most of the students will be at 70. Okay, so that differentiates the best students from the average to the poor students. Okay, so the medium range is what? The medium means what? It is the central tendency of the complete scattered data. We have a data which is scattered all around, and what I'm trying to find out is the central tendency of this data, where it lies, the center of this complete stretch of readings, where the center lies. That is what we will find out by means of mean, median, and mode. I think you know what is mean, median, and mode, and why arithmetic mean will make some sense also, you might have known. So how do we find out arithmetic mean? It's nothing but the summation of all the individual readings, xi, that is, I starts from 1 to n, I starts from 1 to n, that means x1 plus x2 plus x3 plus so on, whole divided by the number of readings. So that will give you the average. Suppose if a cricketer is there, his greatness will be told by he will be scoring in one match 50 runs, he will be scoring some 150 in another match. So finally, if someone asks you, see, if he's playing every day, what can be consistently he can score? If he's asking, you tell me one value by which I can measure him, the best accurate way that we tell him is the arithmetic mean. The total number of runs divided by the number of matches will give you the average of the batsman. Similarly, arithmetic mean will help you to find out the central tendency. So out of a scattered data like this, for example like this, what I'm trying to find out is, I'm trying to find out what is the central tendency. This is done by taking all these readings divided by n. So I'm trying to find out, this is the effect of all these data and a single number, if I'm telling, that is my arithmetic. Now, I'm also defining another term called deviation. Deviation means now I have got the central value or the mean value, so which we will generally see by mu. Okay, mu, or this is nothing but your mean, arithmetic mean. Okay, so now what I'm trying to find out is, I'm trying to find out the deviation, di, or the individual error. Deviation or the individual error. Deviation or the individual error. So that will give you, the deviation is nothing but your xi minus x or mu. You can say that it's mu or xm, mean, whatever, xm or mu or both are same over here in this expression. Clear? So that this is the individual deviation or error, we can say. So if you take the summation of all the deviations, okay, d1 plus d1 square plus d2 square plus d so on dn square, the deviation square, divided by n, the square root, this will give you my standard deviation. So what is the meaning of this? What do you mean by the standard deviation? So from the mean, each individual value, how much it is varying, so the data may be on the line or it may be away from the line. So I found out from the data, so where the central tendency is. So this is the line which is actually is a single value of all these discrete data. Now what I'm trying to do, individual deviation. What is this deviation? What is this deviation? What is this deviation? From the line, what is this? The square summation of the squares of all this divided by the number of readings under a square root will give you the standard deviation. Okay, this is the standard deviation. So I'll tell you a secret, like when we calculate your marks also, and when we grade your marks, how do we do the grading? How do we say the grading is? For example, if you have, this will help you to understand why you get the marks in a different way. So what I do is, I will get from x1 to some x80 number of students, and each one's marks from 35 to somewhere around 90 or something. I will get all these marks. So I'll take the mean of this value and I'll find out the standard deviation of this value. So the mean is basically, for example, 75, and my standard deviation is, suppose, plus or minus 9. Okay, this is what I got the standard deviation. So now, sorry, let us say this is a 70. Okay, so now what does this mean? I say that my B grade is the medium. For example, right now C, no, correct? C is the,
yes sir, C grade.
C grade is the median, and that means the central tendency. So now how do I define my C? I will define my C like 79. Okay, 70 minus 9 is 60. So 61 to 79, my grade is C. Okay, so 1 sigma, median plus 1 sigma is 61 plus 79. So that is my C. And anything greater than this, again another 9 if you add, how much it comes? Around 81. That is my B. In between these two. Likewise. Okay. So if it is A, if you have to get yes, then it should be median plus 2 sigma greater than 2 standard deviation. If the student is able to get median plus or minus more than 2 sigma, then only you should give yes. Okay, so see, we have a clustered data. I'm trying to grade them values. So this is one way of doing it along with the marks. And when it comes to the uses of the standard deviation, so how based on the deviation, we will be trying to take or leave the readings out of the measurement system. So where I need, if I say that my values has to be within the mean, x mean, plus or minus 1 time standard deviation. So the rest of the values I can delete. I can take it out. Only these values I'll be able to take. Clear? So that is the use of having, different uses of standard deviation I'm telling. Why? What it tells you is, it helps us to analyze the data. So where is the central value? How much deviation? How much percentage of values are falling within this deviation? How much are falling outside this deviation? All this will be we'll be able to find from this particular thing. Clear? Any doubts in this so far? So I hope you are able to understand. Try to figure it out. Okay. So now the square of the standard deviation is nothing but your variance. So that is nothing but your variance. So sometimes we also define, this is arithmetic means, so summation is when we take summation values, then we call it as arithmetic mean. When it is a product of that, we will take it as the geometric mean. Okay, so probability in a mathematical sense is linked to the frequency with which a certain phenomena occurs after a large number of tries. So that is what we call it as a probability. Now we have a lot of data. Okay, suppose we have more data that is scattered. That means for the same values, we are getting so much of variation in the data. Okay, because of the randomness in the instrument. So some random errors will create that. So we use binomial distribution, how we can distribute the errors. So whatever I've told you so far as errors, okay, whatever I have shown as errors. So this value is here, this value is, as I told you, the central values like the class in the center will be having more and more number of students. Suppose this is number of students. Number of students, and this is marks, for example. Let us say this is marks from 35 to 100. So there is when we look at this way, if we set a paper very properly, if you don't set a paper properly, what happens is most of the students will be coming over here, 90 to 100, for example. So if the average is there and most of the students are getting around 9 to 100, you will not be having any values over here. The curve will come like this. Okay, it will go like this. So this tells us that the experiment was not done properly. So always the feature of any experiment is it will always follow a distribution kind of a thing. Either it may be a binomial distribution or Poisson distribution or Gaussian distribution. So I am not going to binomial and Poisson distribution. Those who have interest, they can go through these things also, how this Poisson distribution, we have the mathematical formation of how it will be done. So I'm only concentrating on the Gaussian or normal error distribution, which will be designated by the probability of getting a function, getting a value of x is equivalent to, in the whole scatter, equal to 1 by the standard deviation square root of 2 pi e power minus of x minus xm. Xm is the mean by divided by whole square divided by 2 into standard deviation square. So this is how we define the distribution curve. So whatever the values that we get, based on this, we define a curve which is having a central value very high, and at the both ends it is actually a minimum value like this. So this is basically your Gaussian or normal distribution. Any properly done experiment or any properly set paper will give you the binomial distribution. And this is the reason why whenever we are submitting the marks, the board will ask us to show this curve. Whether you got this normal curve, whether you got this Gaussian curve. If you are not getting this curve, that means either the paper is very tough if the curve is like this, or if the curve is like this, it is very easy. So this is very easy paper or very tough paper. So ideally it should be intermediately tough. Somewhat the questions have been tough, and it should always focus on all the students. So the average student should be able to score well. That is the main agenda of setting any question paper for a good teacher. Okay, you should test them. The best student, because of this test, you should be able to differentiate the best students from the average students from the a little lower academical wise, a little bit lower side of the students in that particular subject. I'm not saying that in that subject only we have to define them. We cannot say that this is poor, this is good student. I don't like that. In a particular subject, some may be very good, some may not be scoring that well because of lack of interest or whatever be the reason. All right. So now, there is this Gaussian distribution, which always says that there is a mean that comes over here at the center. The mean, which will be generally comes over here. Sorry. The Gaussian curve is here. So what it tells you is there is always this kind of a distribution where you have a mean, and on either sides we have this values will be varied. For take any data, you will get this kind of a mean value, and on the two sides you will have a variation. Okay, so with the data, whatever you are getting, you should be able to find out your mean and then substitute that in the probability equation, and then you find out a Gaussian distribution curve. So from that, what you do is, for any large number of measurements made to determine a particular value, the random errors are expected to have a normal distribution. So in general, the error will be, because of this randomness, you will always expect to have it to be a normal distribution, given that the experimental system is controlled well. As I really pointed out, if you are controlling the system properly, if you are conducting the experiment properly, even though the error comes, they will always follow a normal distribution. So you will have a X bar value. So that means you have a mean value. And on either sides, you have the standard deviation that you are saying X bar plus sigma, X bar minus sigma. So this is the deviation that I'm talking about. This is the uncertainty that I'm talking about. Okay, this is the range of the error. Again, at this point of time, I would like to differentiate between these two. Error is the deviation of the measured from the measured value. Okay, so input, we have an output. What is the deviation from the input to the output is what we call it as an error. Okay, true value to the measured value minus measured value. But what is the deviation? This range of error. So the error will not be fixed. For each reading, it will have a different error. So what is the range of that error? Saying that from this to this interval, the error is varying for a set of readings. So that is uncertainty. In general, people will use both of them as the same number, with the same terminology, thinking that they have the same meaning. But as a mechanical experimentalist, you should be understanding that it does have two different values. Whenever we are talking about the range of the error for a particular experimental setup, we should say that it's the uncertainty, it's not the error. Error deals with a single reading. Okay, single reading. What is the deviation of that? But range of that error from that system, for that system, is basically the uncertainty. I hope I'm clear. So now, So you have x bar minus sigma and x bar plus sigma. You know these things, I think, from your plus 2 and all, you have been reading this. So as I told you, the probability expression is given by this particular equation. So from this expression, from the mean value, whatever the deviations, 0.1 sigma, 0.2 sigma, from there up to 1 sigma, 1.5 sigma, 1.8 sigma, 2.2, 2.3. Likewise, they have calculated how far this curve is spreading, They have calculated these values based on this. They have already calculated what is the percentage and all. Okay, so that value is generally, we will be talking about those values in two ways. One is how much percentage, how much it is extended, the error is extended, what is the uncertainty of that error, that is one thing. Okay, the another thing is also there, with what confidence you are saying that. Okay, you are saying that 63 point out of 100 readings, 63 readings will follow in this particular range. That is what I can say from this set of experiments. For example, I am in a classroom scenario I will take. If I can say that, so I can say with 63% of confidence that means out of 100, 63 students will definitely score 70. That is one way of doing. You are saying that the central tendency is 70. That is one way of explaining or communicating the values to others. Then we may ask, so 70 is fine, but how many students will get 70? So that is where your confidence level will come into picture. So you have to say that, yeah, there is 70 students, there is a good chance of the students scoring 70. I can say that 63 out of 100 can score that. And there is a good chance of people who is scoring around from in between 80 to 40. So that is uncertainty, 80 to 40. I can say that from 40 to 80, there will be definitely 80% of the students. There is a good chance of 35 to 100. I can say that 100% of the students will be in this particular, 99.9%, 1 or 2 may get failed. So 100% or 99% or 98% of the students out of 100 will score this. So one is actually communicating the number, range of the deviation or error or the uncertainty. Second thing, how much confident you are on a scale of 100. So these are the two things, and the confidence that you are saying is your confidence level or confidence interval. So what people have tried is from these values, they have calculated from these values based on sigma values, based on your standard deviation. What they have done is they are trying to find out what is the percentage confidence interval. Also they have defined for 1 sigma, 2 sigma, 3 sigma. So over a mean value, the percentage of in confidence of interval with which we can say that whatever the readings of the lot, there are many readings, all the readings, 68.2% of readings will fall within this range if it is following a normal or Gaussian curve. That means from the standard deviation plus sigma or minus sigma in this particular total range. Okay, in this particular range, already I used the cursor. That is why I'm not able to use the cursor now. It's not showing. So now from I hope my cursor is showing, right? My cursor is moving, arrow mark. My arrow mark, yeah. So from here to here, that means over a mean value, I can say that 68.2 readings out of 100 will fall in this range. Okay, and if I go further, if the values from the mean may go beyond plus 2 times the standard deviation or minus 2 times the standard deviation, within this uncertainty they will vary by 90. Out of 100 readings, 95.4 readings will fall within this range. That is what we will explain by this particular curve, if it is following that particular. The third one is if it is x mean plus z is 3, so 3 times sigma standard deviation, then I can say that out of 100, 99.7% of the readings will fall within this range. Now it's very simple. Suppose if I want to find out what is it is falling between -1 sigma to -0.5 sigma, -1 sigma to 0.5 sigma. If I want to find out what is this range, what you have to do? So up to here, so if the total number of readings value is 1, if you take half of it, it is 0.5. So you have to calculate what is this percentage and what is up to this percentage. If you take from this to this, the remaining thing will give you the actual value or percentage confidence interval with which you can say that the readings are within this. Okay, so now the confidence interval, the whatever I talked about, expresses the probability that the mean value will lie within a certain number of standard deviation values, and it is given by the symbol Z. So what is the percentage that with which I am saying is basically your Z, and the same thing I have written over here, P of 1, the probability of the values that lie within one standard deviation. Z is 1, suppose, then it is 68.4 or 68.27. Probability of the readings that will fall within the range of 2 times the standard deviation is 95.45, and probability of the readings that will fall in 3 times the standard deviation is 99.73. So this percentage that I'm talking about is nothing but my confidence level for the respective measurement. So this way we will always communicate about the deviation of a set of readings. So the same thing I have given here in terms of if it is Z value is 1.65, Z value is 1.65%, 1.65, then it is 90%. Z value is 1.96, it is 95%. If it is 2.58, 99%, and 3.291, it is 99.9%. Okay, so these are nothing. 3 earlier we took it as 3. If it is 3.2, we are getting 99.9%. Earlier we have taken 2. 2 is what? Around 94 point something. No, so the same thing. Here it is 2.58. If you have, you are getting 99%. So these Z values will be available in your tables, in your what we call normal Gaussian tables. So first you need to find out your Z value. X minus mu by sigma is your Z value. From that you will always find out how much confidence you are able to find out. Next, I'm going to talk about another term with which people will explain or communicate the confidence levels is the level of significance. So what do you mean by level of significance? Level of significance is nothing but 1 minus the confidence level. Suppose if you are saying that 90% is your confidence level, 1 minus 90% is what? 10%. That is your level of significance. Okay, so this is how you will be able to follow the different values. Suppose whenever you are finding out there are different sets of numbers. So if it is less than the number of readings are less than 20, in this expression we will use n minus 1, whatever delta value you are showing here. So Z sigma by n, that will be generally n minus 1. If the number of readings are greater than 20, it is basically your n. Okay. So this problems you can solve it on your own. Let us see what can be the problems like. So you can see here a certain steel bar is measured with a device. Okay, we have a device and I'm trying to measure the length of a steel bar. It has a deviation of point plus or minus 0.5 mm. So he is saying that the standard deviation he has given, it is plus or minus 0.5 mm. When a large number of measurements is taken, okay, so he's doing a lot of measurements, and how many measurements are necessary to establish the mean length with a 5% level of significance such that xm is equivalent to xm plus or minus 0.2 mm. Okay, so he is saying that what is the n, this n, which is necessary to establish the mean length with a 5% level of significance. 5% of level of significance means level of significance is 5%. That means confidence interval is 95%. If you go back, your confidence of 95%, your Z value is 1.96. Okay, so what is your delta? Delta is Z sigma by root n. Okay, delta is Z into sigma by root n. So now you want to find out how many measurements I have to take. Therefore, n root n is equivalent to Z sigma by delta. Okay, and therefore your n is equivalent to Z sigma by delta whole square. That will give you your 25 readings. So minimum 25 readings you should take, such that you will be able to get the delta, this whatever the deviation we are getting, it should be around 0.2 mm. If I want to get, so your n should be 25. Okay. Similarly, we also have the resistance of a copper wire that they have taken for different times. They have taken what is the best estimate for the resistance with 95% confidence. That is the question. So what is 95% confidence again? 95% confidence, what is the Z value?
1.96.
Yeah. So Z value, you know 1.96, and you know you can find out from this what is the mean, what is the standard deviation you can find from this. Okay. Substitute that into the expression, and then you'll find out what is the best estimate for the Z value of 1.96. 1.96 is basically what, if you go and look at that, it will tell you what is the percentage confidence of that. So Z is equivalent to x minus mu by sigma, this value they're asking about. Okay, so you can find it out from that particular experiment. So please try to, I'm given a solution, please try to solve these things. Okay, and then we will continue with this particular thing. So now we have found out two ways. One is measuring the standard deviation, that is one thing. And we also found out another thing, like how do we estimate, how do we estimate the random error with normal or Gaussian curve. Okay. So this is what we have seen yesterday. So you are sure now that from a particular instrument, this is what about, I'm talking about gross. It's not an accurate way of solving it. This we have studied yesterday, plus 4 point. So now we will move on to the uncertainty analysis, which is one of the most important thing that we have to conduct. As a PG student or an experimentalist, you have to always tell what is your measurement. Okay, what is the uncertainty in the measurement? What is the range of the error that you are going to get out of the instrument? Okay, so far, sir, what we have found out? What we have found out so far is how to estimate the deviation or the error, each individual uncertainty of a particular instrument. That is what we found. Okay, so for a pressure measurement, how much is the error? For a thermocouple, what is the error? Okay, so out of the readings, how do we estimate the deviation? That is what we found out. But overall, for example, if you are finding out power, so you have got plus or minus 2 voltage. How to estimate this? That is what we found out. How to estimate I? This is 0.2 amperes. So this deviation, how to find out? That is what you have so far found out using statistical analysis or whatever. What is this value? You are able to find out this one. But if you want to find out power, which is a function of E and I, for example, it is a function of E and I. So on a common sense basis, what I tried, P max and P minimum I found out, and then that error I have found out that this is maximum and this is minimum error that I have. This is basically a gross value. But if I want to find out what is the power value, how it is varying, what is uncertainty in the measurement of power when the instrument that is measuring voltage is having a deviation like this, and if it is a current, it's having a deviation like this, how do you estimate that? individual deviation of this much, how do you estimate that? So for that, we are calculating uncertainty. I hope I'm clear. Okay. So as I told you, error is the difference between the measured value and the true value of the thing being measured, and uncertainty is the quantification of the doubt about the measurement result. So we are talking about the range. Okay. So whenever possible, we try to correct for any known errors by applying corrections, by using calibration certificate. But this is for reducing the error or negating the error at all, completely out of the equation. So that is what we are trying to do. But always errors will be there which we don't know, and those errors are the sources of uncertainty. So those will create a range of errors. Okay, so as I told you, uncertainty, it will be generally expressed with two parameters. One is the range of the error, width of the margin or interval. Second one is the confidence level. Okay, how sure you are able to tell that the true value is within this margin. So that is your confidence level. Okay, so now I'm giving you a small example that we have 20 centimeters plus or minus 1 centimeter at a level of confidence of 95%. So someone is giving this to you. So that means what? The statement is saying that I am 90% sure that the stick is either 19 centimeter, 20 minus 1, 19 centimeters, or 20 plus 1, 21 centimeters long. Okay, so out of 100 readings, 95 readings will definitely show that it will be in either 19 or 20 or 21. In this range, whatever be the value, 19.1, 19.2, whatever be the value, lies within this range. I am saying that 95 out of 100 will fall in this particular range. Okay, so in such a case, how do we estimate? This is individual measurement, one length. But if you have a calculated result, that means you are having R, which is a function of x1, x2, x3, xn. Each is a different instrument you take for easy understanding. This is an instrument. This is an instrument. Whatever the value that I'm getting from here, all these individual deviations are measured by statistical analysis or calibration curve. Okay, and that I have to incorporate into this and finally find out what is the uncertainty that I get in R. What will be the uncertainty in R? If you have to estimate that, then a famous person has given this famous person name is McLean and McClintock. McLean, CLIN, and then Clintock. KLINTOCK. So this method is given. So this is what we generally follow in our experimental setups, in our macro experimental setups. This is the method we use to follow for uncertainty analysis. So this is a must. You have to publish a paper. You have done some readings and measurements. You have to say that your measurements is having an uncertainty of this range with this percentage of confidence that you have to say. So now we will briefly see, your time is another 10 minutes is there. Okay. So what we do is let WR, what I'm trying to say is let WR be the uncertainty of in the result. Finally, R is having an uncertainty WR, and W1, W2, W2, Wn, these are all the individual uncertainty related to X1, X2, X3, so on respectively. X1 is having a deviation of W1, which is measured by statistical method. X2 by W2. X3 is having W3. So on, Xn is having Wn. So if they are like that, and if this function, if R, the final form of this final variable is a function of all these variables, you have to do this by saying that dou R by dou X1. The partial differentiation of R with respect to X1 into W1 whole square plus dou r by dou x2 into W2. W2 is the deviation in the measurement x2. Similarly, dou r by dou x3 into W3 is the x3, deviation of x3. So on, this whole square under the square root of 1 by 2. This will give you the deviation of this r value, or uncertainty of this r result. So now how this r is it an additive function, or it's a productive function, or it's a they're related in the form of a division? Based on that, this partial differentiation you have to modify, and then accordingly you will get the equation for the uncertainty. Okay, so it may be temperature, thermocouple is used to measure, and thermocouple deviation is W1. X2 is pressure, whatever the deviation in pressure you have to put over here. So likewise, all the individual things are squared up, and then under a square root if you take, you will get the uncertainty, that particular r. This is the method proposed by McLean and Clintock, and you can see in any most of the papers they will suggest this. I have written, sorry, the spelling is McKline. I have written wrong, not C, Kline, and this is not K, this is C. Okay. For example, I'm giving you some examples over here. Suppose if the result of, suppose a function I am taking r, which is related to the individual measurements x1 with the power a1, x2 with the power a2, so on, xn power an. For example, this is the way this r is having its variables related. The relation between the variables and the product, the value is this. Okay, so now I want to find out what is the uncertainty in the r. X1 is the measurement and a1 is nothing but the power of that. Okay, so now when we perform the partial differentiation, dou r by dou xi, for example, I'm taking xi here, xi whole power ai, somewhere here. I'm just taking dou r by dou xi. It is nothing but x1 a1, x2 a2, then ai xi ai minus 1, so on, other things are the same. So all other things are remains constant, only this time I will be taking a differentiation. So ai xi ai minus 1. Now what I'm doing, I'm dividing both sides by r. So what is our r? So r is 1 by r here. Now this one is again x1 dividing by r, that is nothing but x2 a2. This is xi ai, so on, xn an. Okay, so now xn an, this one will get cancelled, x1 a1, this will get cancelled. So if I write xi ai, this will go, and ai by xi is what is left over. Okay, so now this value, if I substitute in this expression, what is this expression showing? Omega r is equivalent to dou r by dou x1 into omega 1 whole square under square root. That is what we are seeing here. So now what I'm trying to do here, I know that dou r by dou xi 1 by r is ai by xi, correct? So now that expression, if I write, this is the omega r that we know from the previous expression. So here whatever I am dividing on both sides by 1 by r, so it will be 1 by r, it will be 1 by r. Okay, dividing both sides, so it will become omega r by, or deviation r by r is equivalent to what it will be. This is nothing but ai, this whole 1 by r dou r by dou xi is nothing but ai by xi into omega 1. Similarly, a1 by x1 into omega 1, a2 by x2 into omega 2, so on, a by an by xn omega n also. So that I have written in the form of I is equivalent to 1 to n sigma under square root of ai omega xi by xi whole square. So if I know the values of a1, a2, a1, so on, if I know the individual deviations of these values, uncertainties of these values of x, then automatically if I summate all of them, this product of all of them squared under a square root will give you the deviation into R. Okay, so this is how I have to use uncertainties for product function. So it is in the form of a product, a function. So there I will use this method. Okay, suppose if it is in the form of an additive function, so the total function is in the form of additive, in the additive way. So you can write it that it's sigma ai by xi. So partial derivative by dou r by dou xi is basically your ai. Okay, so ai. So when you substitute this into the expression, you are getting this value as ai into individual deviation xi whole square, a1 wx1 whole square plus a2 wx2 whole square whole under the square. This will give you the uncertainty in R when the measurand value is a function of is in the form of an additive function. Then we will use this formula. So you have to be, the problems will come from this only. So whatever the whether it is given in the product way or whether it is given in the additive way, based on that you will calculate this. Okay, so one example I have given here, the uncertainty analysis of a certain copper wire is given as R0 into 1 plus alpha t minus 20. You can see over here. Okay, so this resistance R is dependent on what? R0. R0 is what? The resistance at 0 degrees centigrade. Alpha, coefficient of expansion. T is the temperature. So it is depending on these factors. So if you take that, it will be an additive function, R0 plus R0 alpha t minus 20. And he is giving that R0 is equivalent to 6 ohms plus or minus the mean value he has given, and 0.3% is the deviation. Individual deviation omega n is this much, or plus or minus 0.3% at 20 degrees centigrade. Similarly, alpha value is a constant value which is measured by a measuring instrument. Its deviation is how much? Plus or minus 1%. And the temperature of the wire is 30 plus or minus 1 degree centigrade. Okay, so what is asking is calculate the resistance of the wire and its uncertainty. So what is the value of R and what is the uncertainty? If uncertainty is not there, we will put these values into this and directly get the resistance value. Okay, so the nominal resistance is what? R is equivalent to, they have given that 6. Okay, this 6 ohms. So R0 is 6. 1 plus alpha value is 0.004 into T value is 30 minus 20. This is giving 6.24 ohms. That is your nominal resistance R. Now, how do you find out the uncertainty in this? The uncertainty is dou R by dou R0. Okay, partial differentiation. It will be giving you 1 plus R0 by R0 is gone. So 1 plus alpha into T minus 20. Okay, so this is the value of dou R by dou R0. Dou R by dou R0. First value. The first value, dou R by dou R0 into omega 1 square or the deviation whole square plus dou R by dou x2. So same thing we have to see. So first one is dou R by dou R0, 1 plus alpha t minus 20. So dou R by this one will give you 1 plus alpha t minus 20. So directly you got 1.04. What is this? This is only the value of dou R by dou R0. Similarly, dou R by dou infinity. So next term is dou R by dou infinity. So when you define by this, it is nothing but R0 into t minus 20. So this first value is not there. So therefore alpha value we will take out, and this is R0 alpha t minus 20. Therefore alpha is gone, R0 into t minus 20. So that is 60. Second term also has come. Third term is dou R by dou t. So dou t is here. So R into R0 into alpha. Okay, t term is 1 and this is a constant, it is gone. So 6 into 0.04, that is 0.024. So now we got dou R by dou R0 into its individual deviation whole square plus dou R by dou infinity into its individual deviation whole square plus dou R by dou t into its individual deviation whole square under square root will give you the uncertainty omega R. Okay, so now your omega R naught is given by 0.018 ohms. Okay. Omega alpha, your deviation. So you have omega into R naught. So what is that? 0.3% he has given. If he's given some value, that's fine. But he has given in terms of percentage. For 100, it is 0.03, 0.3. Okay. For 6, how much? Okay, that is 6 into 0.3 divided by 100. So that will be 0.018 ohms. That's why I've written omega R naught or individual R naught value. So it is 0.018 ohms. Don't get confused here. It is percentage. It is individual deviation at 6 ohms. This is 0.3 percentage. This is for 100 ohms. 0.3 is the value. So 6 ohms, how much? Similarly, alpha 0.04 degrees centigrade, they have given 1%. So what is the variation for 0.04 degrees? That you are getting 4 into 10 power minus 5 per degree centigrade. Similarly, for omega t, he has given 30 plus or minus 1 degree centigrade. He is not given in percentage, so it is directly 1 degree centigrade. So whatever the value 30, it is only by 31 or 29. So directly he has given 1 degree. So that's why I have taken 1 degree. Now substitute this value in omega r. Omega r is nothing but the uncertainty in R, resistance. So that is nothing but dou R by dou R naught. Okay, so dou R by dou R naught into xi whole square. Okay, dou R by dou R naught square into omega I square plus dou R by dou alpha square 60 square into the deviation square, that is 4 into 10 power minus 5 whole square plus dou R by dou t square, which is nothing but 0.024 square into omega t is 1 square under square root will give you 0.0305 ohms. So that therefore we can say that the value is R is 6.24 plus or minus 0.0305, or if you convert that into percentage, you can say that 0.49%. Clear? There is another problem given over here, whatever we have done in the earlier class. So it is P equal to E square by R, P equal to E, individual deviations are given. And from that, you can find out this particular thing. Similarly, I have given another problem here with the building and all. You please try these problems. Okay. So with this, I'll try to stop for today's. Sorry, I've taken 4 minutes extra. So I hope you are able to understand what I'm trying to convey. I hope it's clear. Okay. So these two PPTs I will upload. I will send to you, including the third one. That the last class I've only talked about the three slides only. That's what I haven't uploaded that. But today I will send through email first. So please do sit and try to solve this problem. This kind of problems you can expect in the examination. Okay. Any questions, guys? I'll be happy to explain. My video is not. Any questions? Is there anyone in the class? First of all, no doubt, sir. Amarnath, is it very clear, or I basically?
Yeah, sir, it was clear.
Yeah. So whatever you in TE record, it is 45 cc or 10 cc. See, please take that as 10 cc. It's not 45 cc. In general, for any engine to get to steady state, you have to allow that fuel consumption to around 45 cc. Okay. So that's why in the tabular column they have given 45 cc. Am I clear? So, but in our example, we have taken 10 cc because, you people are not there and the technicians are saying so many issues and they're not giving correct reading. So we were also, if you are here, you will do the experiment for a long period of time, so you can take the readings up properly. But now they're giving some values and we are sending you that. So don't worry about the readings too much. We are only taking for 10 cc, but ideally you have to take for 45 seconds. As I told you, 10 seconds, there will be fluctuations in the engine, right? So obviously you will have some error. So in order to reduce that error, they suggest that you wait for a considerable amount of time. Take the time for 45 cc so that any error will be reduced. Okay, so when you are making measurements also, you will not be allowed to, suppose the engine is started, you will not take the readings immediately. You will wait for some time, because it's all of a sudden it's started. There will be transient effects, unsteady effects will be there. It has to get it should get to a steady state, then only you will take the values. So whenever you are studying any particular value, there are two ways of doing that. One is the steady state mode, and another one is the unsteady state mode. Okay, so generally steady state will be it's not very complex, it is easy to study, but unsteady state becomes important in some cases, in some scenarios, in some applications. So therefore, you always, any problem you take, there are two ways of looking at it. One is a steady state, another one is unsteady state. Even when you are studying about the ordered systems also, zero order system, second order system, you have one steady state term and the other one is an unsteady state term. So in every place that will be this. So for this example, you take 10 cc because we have calculated at 10 cc. So you just take it for 10 cc, make the calculation for 10 cc. And related to the readings, for motoring test and all B section people, you need not worry. Next Friday onwards, I will give you time to the next week, because I don't want you to lag far behind, and anyway, both experiments are similar. So I just thought of giving you completing that in one single session so that you will not be lagged behind. So now you are behind by one experiment. Otherwise, you will be behind by A section by 2 experiments, which I don't like. So you are in line with them. So now next week onwards, if you can arrange the classrooms to be, lab to be for A and B sections on the same day, so one time it will be done. Okay, you will not be lagged behind. Okay, so that is what we are actually looking at. Let's see what we can do. Next week when you come, directly we will go to the 4th experiment. In one session, everything will be explained. So the next day you can have the other lab as a complete one section. So it will not be 2 sessions. I hope your whatever section was over, and next week onwards it's vibrations. Huh? What is the other lab? Some other lab is getting started. And GRK Gupta sir has already talked with the professor and he agreed. So we are looking at Sahil, MTM. So now we are planning that we will have that experiment, our lab experiment, thermal engineering on Thursday. So anyhow, I will give you some time to submit the record. That's not a problem. Only thing is, see, in that experiment, what you are trying, if you understand very clearly, in one experiment, to find out the frictional power, what you are trying to do is you are running the engine. That means fuel is injected, air is compressed, and then the diesel engine starts. And then by applying some power from load, if you look at it in the normal general way, you can imagine that you are going on a Splendor bike, for example. It's a petrol engine, but suppose if it's a diesel engine, you want to go at a constant speed. You are not varying your speed. But when you ride the bike alone as a single person, or with another friend of your 2 persons, or with 2 more persons, that means 2-3 people are sitting, with a constant speed you are riding, how the vehicle performance is changing, how the brake power is changing, how the fuel is consumed, how the indicated power is varying, how the brake thermal efficiency. So that is what you are trying to do. You may ask, sir, why this constant speed test only? Brake power is 2 pi nt by 60. Either you can vary. There are 2 factors based on which this brake power is changing. Brake power is nothing but the power that you are getting at the wheels. So that is what is getting changed. So now you may ask, sir, why only those? There are only 2 parameters, N and T. Either you can keep the load constant and vary the speed. Either you can keep the speed constant and vary that. That is why we are doing this kind of test. So now the first case, what we are trying to do is we are trying to keep the rated speed at the same. Okay. So when one person is sitting and you are going along with the speed of 60 kilometers per hour, And when another person also sits, if you want to cruise along with 60 kilometers per hour, fuel will be consumed more. If it is 3%, it will be consumed even more. So how it will vary? So the fuel consumption efficiency, that is what you are looking at. And when more and more loading you are putting, your frictional power also gets increased. So how much is the frictional power? So to find out the frictional power, what we are trying to do in the first experiment, in the yesterday's experiment, you are giving a constant speed of 1500 RPM and loading in general persons, number of persons sitting, you are putting by means of a electric DC shunt dynamometer, you are loading that electrically, you are loading. So when you are loading, each time your fuel consumption will be very fast. So as you increase the load, your fuel will be consumed very quickly. So the time is lesser. So from that, you are getting your fuel consumption kg per hour divided on the y-axis, and then with brake power, you will be getting some curve, and when you extend that curve, you are getting your frictional power. Okay, that is one way. That's a very crude way. That's called as Whelan's line method. It's a very crude way of looking at it, because depending on where you have taken the tangent to find the intercept, your frictional power is changing. So on what basis you will actually estimate what is the correctness of the frictional power? You never know. So for that, what sir has told you is either you take a linear portion and extend it such that you will have an x-intercept. That is one way. Okay, for that you have to take the scales properly to get the linear line and all. If you take the scale very closely, obviously you will get a very steep line, and then you will never get an intercept. Suppose if you are taking the x scale to be somewhat extended, then probably you will get a chance to actually have a linear line, and that line can be extended to get the x-intercept and all. Okay, so that is one way. Otherwise, is 75%. At 75%, you take the load, and then from that point you try to draw. Anyway, whatever be the frictional power you are measuring from your Whelan's line, it should not be beyond 25% of your brake power. That is what the basic line. If you are getting an intercept much beyond 25%, then nobody will be interested. So if an engine has more than 25% of frictional power, then it's a very, very low efficient engine. Or it cannot be very low. That is also wrong, 0.1, and that is all wrong. So it has to be somewhere between close to 25 to 20%. That is what Professor has explained in the last class. There is another way of looking at it by doing a motoring test. Okay, in a motoring test, what we will do, we will not run the engine by fuel or by this one. What we will do is, we will use the dynamometer as a motor. Motor means what? It takes electrical power and rotates the shaft. So what we are trying to do is, we are trying to rotate the shaft by motor and then applying load on it. Okay. When the shaft is rotated, what happens? Because since the shaft is rotating, the engine will move up and down. So the piston will move up and down, but there is no combustion that is taking place as it happens in the other case. So now what we are trying to do is, you are taking the RPM versus your torque. Okay, so what is the torque and what is the RPM? Based on that, you are trying to, for different torques, you are taking different powers, and then you are trying to draw a graph, and from that you will calculate the brake frictional power from this brake power, speed versus your brake power. Sorry, speed versus your torque. If you put that into the expression, whatever the power that you are getting is nothing but your frictional power. So you are getting at 1100 frictional power at 1100, 1200, 1300, 1400, and 1500. So already we are conducting the experiment at 1500 RPM through Whelan's method. We have already find out the frictional power. Now you have at different speed, what is the frictional power you have from the motoring test. Then you can kind of sit down and look at those two things. By Whelan's method, how much you got. By the motoring test, how much you got. So what can be the reason? For example, let me put it that way. Ideally, according to me, if an engine actually runs, that means in a constant speed test, whether the friction has to be more, or in a motoring test, the friction has to be more. Which one should get more? So those who doesn't have interest and they want to live, they can live. They're free. The class is over. No problem. What can be the reason? I mean, which one will have more friction? I'm telling you, in one case, constant speed, there is a combustion taking place. Combustion means temperature of the materials are increasing. So now you can tell me where you can find out. In the other case, there is no combustion, there is no temperature. Which case will have more frictional power?